All right. So you'll have to unbox the pH meter. It's a LabQuest system. So maybe some of you have used LabQuest before. LabQuest, you can use multiple probes for this. And the probe we're going to use is the pH probe. But we have to plug it in. This is also battery operated, but we'll just use the AC cord here. And the batteries are probably charged. They've been sitting for a long time. And so just plug in the AC cord. And then you can turn this on. There should be a power button here on the top, a red button. In the top left. Okay, the next thing we're going to look at is in the cardboard box here. This is the probe we're going to attach to the LabQuest system. Okay, this probe is sitting in a liquid. The liquid is just to condition the detector part of the probe. Let's take a look. What you can do is twist this off of here, or you can loosen the cap. If you loosen the cap a little bit, it should pull off easily. Then take a look at the end of the probe tip. Do you see it? So go ahead and remove that. Don't spill the liquid here. Okay, what do you see at the end of the probe there? Yeah, a bulb. Yeah. It's very thin. It is a ball. Inside that ball is liquid. And so you could just put this back in there. Talk about that glass. The surface of the glass is treated so that it's sensitive to hydronium. And so what can happen is this. What can happen is, let's say you get a bunch of hydronium collecting on the outside of this. What that's going to do is, if a whole bunch of hydroniums are collecting on the outside of the glass, that's going to increase the positive charge on the outside. On the inside, there's a fixed amount of positive charge and a fixed amount of negative charge. And so whenever we have a difference in charge, it creates something called a voltage. And what we're measuring is the voltage. The voltage is very small. It's millivolts that we generate. But what we can do is we can calibrate the millivolts to a pH reading. And so what we're going to do is we're going to just go ahead and plug this in to port on the side here, or channel 1. And so you use the smallest number channel. We only have one probe, so we'll just plug it into channel 1. And then it should recognize it, and you should see the pH reading of the liquid in there. No, just delete it. All right, so you're getting a real-time pH reading there, correct? Okay. Now, how do we know that, what's happening here is we're getting a millivolt reading, and that's the LabQuest system is converting that into a pH reading. Now, how do we know that's an accurate pH? It's like you go to the store, or if you go nowadays, you buy gasoline, right? You go buy gasoline and the pump says 1 gallon. Well, how do you know that's reading accurately? Are you really getting 1 gallon, or are you getting a little less than 1 gallon? Obviously, they probably wouldn't give you a little more than 1 gallon, so then they lose money, but maybe they're giving you less than 1 gallon. Even though it's reading 1 gallon, how do you know it's reading accurately? The same thing when you go to the supermarket, right? And you're weighing some vegetables, how do you know that's reading accurately? Yeah, you have to trust who, though? Do you trust them to make sure it's reading accurately? Well, it turns out no. In fact, the LA County comes by and checks it to make sure it's reading accurately. Right. And so we've got to do the same thing. We don't know if this is reading accurately or not. And so how can we check if this is reading accurately? Well, you've done that. Oh, well, actually, you might not have done this before. We check everything. Even our balances over here, the scales, we check to make sure they're reading accurately because sometimes they can drift, be an inaccurate reading. If that happens, we need to reset it. Do you know what that process is called when we check the accuracy? Calibration. And so the first thing we do when we're working with scientific instruments is we make sure it's reading accurately by calibrating it. If we don't, that leads to something called a systematic error. It's always weighing too high or it's always weighing too low. That's a systematic error. And it's our job to get rid of all systematic errors by properly calibrating our equipment. Now, that's different than random errors. Random errors you're going to encounter. Random errors are more difficult to get rid of. The way we get rid of random errors, or try to get rid of random errors? You're right, doing multiple trials. The more trials we do, then sometimes we get a high reading, sometimes we get a low reading. And then we'll just average it out, hoping that the high readings cancel out the low readings and we get the actual true value. But to get the actual true value, it takes like an infinite number of measurements, And so infinite number of measurements is too difficult. So typically we take how many measurements to get something statistically meaningful? 3. 3 is probably the biggest payoff, as far as getting a decent average versus how much time it's going to take you. Obviously, if you do 4, 5, 6, 1,000, it's better. But the payoff gets smaller. Let's say I did 1,000 versus 1,001. Is there a big difference? Or 1,000 and 1,003. Is there a big difference? No. And so it becomes less and less significant with the greater number of readings we do. For this, we're just going to take one reading, I think. We're going to take multiple readings because everybody can do it, and then we can see what people get, then we could average that. So the first step is to calibrate. So we need something of known pH that we can use to make sure it's reading correctly. And so let's just see if this is still calibrated by getting something known. Do you think these small plastic beakers? Yes. Okay, if you look at the small plastic beakers, they're going to be labeled pH 4 and pH 7. Okay, these are expensive solutions of known pH. These are known to 3 sig figs. These are called buffer solutions, and this one has a pH. What do you think the temperature is today? Okay. In Celsius, what do you think the temperature in Celsius is today? 23? 25 is like 77. Do you think it's 77? We actually have a thermometer now. Yeah, this thing's a barometer. Actually, I can't even see the mercury in here. The lighting is. Do you see any thermometers back there? Right, it's about 20.9 degrees, 20.8 degrees. And so that means this solution, the pH changes with temperature. Why does the pH change with temperature? Because K changes with temperature and that kind of thing happens. But anyway, we're good at, the pH of this is 4.00. That's good to 3 sig figs. You can read it on the label here. Okay, at 20 degrees C, this one's not 7. This one's 7.02 at 20. And so 7.02, 4.00. Okay, this is what we're going to use to calibrate. But the thing is, and these buffer solutions are resistant to contamination. And so what we do is normally we never pour. Let's say I pour some solution in here, we never pour it back in because that contaminates this. But buffers, one characteristic of buffers is they have a stable pH. So even if there's some contamination, they maintain a stable pH. And so we're going to, because the solutions are kind of expensive, we're going to reuse them. And so all you need is enough to cover the glass bulb. And so just think how much that is. It's not much. And so don't use too much. And so what we're going to do is cover the whole thing. The glass bulb. So like a centimeter's worth. Okay, look at the pH here. What's your pH reading currently? Did you plug in the probe into channel 1? Let's take a look. 3.99. So it's closer to 4. Yours is close to 5. Okay, we're going to start off with the pH 4. And this is the way we do this. So I'm going to just get some buffer here. I don't know if the buffers have an eye hazard. Acetic acid, acetate. Acetic acid, acetate, that's okay. This is vinegar. It'll sting a little bit, but it won't cause permanent damage to my eyes, I think. Otherwise, I'd wear my goggles. Probably should wear my goggles. Okay, I don't know what this solution is in here, so it's probably a good idea. I don't want to get this in my eyes. Now, the way the procedure goes is we get a big beaker. And this big beaker we call waste. So you could use like green tape or, we aren't really using any big beakers. So I'm just going to label this waste with a Sharpie. Yeah. No, you're taking out your own. Okay, now what I told you, these are resistant to contamination, but we try to avoid as much contamination as possible. This is the problem with goggles and the mask. The problem with the goggles and the mask is they fog up like this. So I have to adjust it. Maybe, I don't know, masks might be, optional someday in the future. It doesn't mean that you're forbidden from wearing them. Of course, you can wear them. A lot of places they wear them all the time, like in Japan. All right, now the bulb is contaminated with the storage solution, and I could put it in here, but I don't. If I don't have to contaminate it, I don't want to contaminate it. And so what I'm going to do is I'm going to get a wash bottle, and I'll probably with this wash bottle, I'd probably dump whatever you have in there and put some fresh DI water in there. And then what I'm going to do is I'm going to wash that storage solution off into the waste beaker here. And so I'm just going to get a thorough rinse. And now the bulb is wet with DI water. So the bulb is wet with DI water. I don't want to put it in here still because that's going to contaminate this with water. I don't want to contaminate it with water because what ends up happening is dilution. And so let's say you have 6 molar acid and you're dumping water into it. It's not going to be 6 molar anymore. It's going to be like 5 point whatever. And so what we're going to do is take a Chem1B, which are these lint-free tissues here. That's like $15 a box right there. So it's not like Kleenex tissues or something like that. And then we're going to dry this off like this. Okay, try not to break the bulb. I've never seen anybody break a bulb. but I heard somebody broke a bulb in a high school laboratory, and the teacher made the student. It surprised me, because glass, glass eventually gets kind of brittle if you don't, anneal it. And so if you keep banging the beaker on the counter, eventually it's going to. Okay, so I washed this and dried it, and now what I'm going to do is mine is reading like 4 point something. I'm going to put it in here, and it should read 4.00. And so what I'm going to do is I'm going to swirl this, because I couldn't completely dry the bulb, and let it equilibrate. And let's see, what is it reading? 4.01. So close. It's so close, but it's off a little bit. You see that? It's supposed to be 4.00. Should I say just close enough? Oh, it changed. It's 4.00. Okay. Let's say it wasn't reading 4.00. Let's say yours was way off calibration. If yours was way off calibration, this is what we do. Mine might not need any calibration. Okay, what we do is this. There's a little stylus here that you can use. And we'll go to sensors. So, but while we do this, why don't you come and get a little bit of the pH 4 buffer into your little plastic beaker, enough to cover this. If you have a ring stand, what's helpful sometimes is to set up the ring stand with a clamp so that you can hold the pH probe up. You don't have to hold it all the time with your hand. So that's what I'm going to do. Yeah, you can grab the other one too. So you might want to listen, get a utility clamp for your ring stand so that you can suspend the wire so that it can hang normally. You don't have to hold it all the time. But one thing you never want to do is you never want to let the bulb dry out too much. If the glass bulb dries out, it becomes very unresponsive, the pH meter. And it's not good because it takes time to condition the bulb. And so you can leave it in air for a little bit, but not for too long. What you want to do is you always want to leave it submerged in some liquid. Okay, the calibration should last the whole lab period. So can you do this? Can you pour back your buffer solution since we're on low budget here? Can you put the buffer solutions back? Otherwise, we throw it away. We wouldn't do that when we have the money. But you don't want to see your tax dollars increase because we have to buy lots of buffer solutions. I just don't go into city. What is this up for?
Makes this like able to not get.
We're going to talk about that in great detail. Hopefully. Okay, what you want to do is you want to test, does the pH probe fit into a test tube? So do you have a test tube that the pH probe will fit in?
Once you're done with your water.
Yes. Actually, you don't have to. Just leave them. Or, you don't have to rinse the test tubes with the buffer solution. Even if it dries out a little bit, that's all right. Do you have a test tube? You don't have a test tube that the probe fits in?
No, I don't.
Yeah. All right, then get a small beaker. And we're going to get some ammonium chloride solution. It's in the hood, one of the hoods. I forgot which one. Fill a small beaker up with ammonium chloride, enough to cover the probe. Oh, here, no, let me, is there a transfer beaker there?
Yeah.
Are there? It's 0.1 molar ammonium chloride is not hazardous. It's generally regarded as pretty safe. So if you don't want to wear your goggles, it's okay. This one's not absolutely mandatory here.